during the while loop, right, over here, we need to wait, and everybody needs to wait. So we don't like to see that happening. So fskin's implementation is blocking when it calls this particular u.cat character. So we want non-blocking code. How are we going to solve it? We use an interrupt service routine. So the idea is that we do not want this while statement. We simply want to say, if the received character is complete, hardware event triggers, and the ISR that corresponds to that knows that it can read a character. So let's do this. So let's make it a little bit more complex, in the sense that I would like to write, say, a string. How am I going to do that? So a couple of programming things over here. I would like to create a string that, I have my console, I'm going to type stuff down, and then I hit the enter character, and the string that I typed should get read into this R buffer. It's an array of this size, and I've created here with define what this actually means. So this is just a keyword now, right? That takes, after pre-compilation, the value 50. What we're going to do is we're going to create a buffer, and the buffer is going to be read, it's going to be filled one character by one character, and I essentially have an index to where I have filled it, which is this R index. That's that variable that we use. And then I have a very different type of variable that tells me when I've received the enter character, because then I have finished as a human to type in my string, and I have received the whole string, and now I'm ready to do whatever I want to do in my main program. So that's what I would like to do. Now notice, you see here a volatile over here. Now this is the first time that you've seen this. Why do we put it there? So first of all, the volatile keyword warns the compiler that the declared variable, which is this already, can change at any time without warning, and that the compiler shouldn't optimize the array no matter how static it seems. Okay, let me explain you something about compilation. In the main program, this already variable will never be changed. It will not be set to 0, or it will not be changed its value from its default value other than 0. The only spot where this changes will be in our interrupt service routine. But the interrupt service routine is never called from the main program. It's called by the, it's essentially activated by the interrupt controller. So the compiler thinks you're never really using this already. It's always equal to 0, because they've brought smartness to compilers to compress the binary as much as possible and make programs as efficient as possible to execute. So the compiler will just take this already out and replaces it by 0 everywhere, and then your program will fail. So you have to tell the compiler that you do not want it to remove this variable. So that's what that volatile means, and you will notice that you have to do that when you program timers and other things. And on the safe side, I sometimes maybe use this keyword a little bit too much. But here we have the cat string. So if I call the cat string procedure, I say I'm not yet ready because the string has not completed. If I set this to 1, then I've received the full string that I've typed in. The R index is set to 0. I'm at the 0th position in my buffer. I've not seen anything yet, and I'm ready to receive my first character that I'd like to put into that 0th position in this particular buffer. So buffers are all from R buffer 0, R buffer 1, 2, up to 49. So now, look at this. I'm going to enable the interrupt enable for the received character complete in this register. So at that particular moment, I'm enabling the interrupt. So if a character comes in, what's going to happen? So I will do that in a moment. Then, but then the interrupt service routine is obviously going to execute. So in the larger context, right, how am I going to use this? I'm going to do all my initialization. And the important one over here, so initializations, the important one over here is I enable a global interrupt. That is what I'm doing. If in my while loop already is equal to 1, meaning that a string has been received in its completion, then I can say, well, when the task interpret the read buffer, something, I'm not specifying it, but it could be one of your finite state machines when you were processing email addresses, for example. That's what you do. And after that, I may want to call again a get string. I can call this functionality. In this particular layout, as you can see, this is running forever. If already is not equal to 1, this is not even called, and all the characters are being received at the background by the interrupt service routine, and I'm going to explain in a moment. And all kinds of other stuff can execute, so it's non-blocking. Everything can keep on going. And very different, another statement could be said here, like another condition. This is one condition, say some condition 2 is met, all of a sudden, then some other task can be executed, and then I may reset that condition to some kind of default state, and I can have more of those. And later on, when we talk about task-based programming, this is exactly what is meant by that. We will see that you can have a lot of tasks that can all be called whenever their conditions are being met. And they're not blocking to one another, they only execute if they're ready to execute, if they're really ready to do some computation. So there's no idle computation time. So this is the general setup, actually, that we have from now on in our coding. We do initializations of all the registers, the interrupt enable masks are set right for, in our case, for the receive complete, for the UART. Then we enable all the interrupts that we have set, and so on. Now, as I said here, if we call get string, well, the buffer has not even started reading. The index is set at 0, already is set at 0. We have not received a return button by the user that says I've typed in my string. So you enable this interrupt service routine, and from that moment onwards, this while loop, here we have a get string executing, so the while loop can be interrupted by that interrupt service routine. So what does it do? Well, we could take the code that is in the UART library and translate it all into the ISR. Here, I've only taken a subset out of that, not all of it, but you can have a look in the original UART get character, and you can add more to this, but it's a very simple line editor. So how does it work? If this interrupt service routine is called, then I know that there's something ready for me. So this register has some character that I put in R character. I'm going to interpret it. That's the line editor's task. If it is, an enter character, if it's not equal to the enter character, then I've received something else. For example, I received a backspace in the ASCII2 table. You will see 127. Don't ask me why, but if you put in /b, which should also stand for backspace, then it doesn't work in our Atmos Studio compilation. But this actually does work. At the time, it took me quite a while to figure that out, actually. But once this backspace is read, what do? We have already received a bunch of characters in our buffer. We filled it up to our index. But we'll go one step back because we are erasing as a user the last character. So that's what this happens. So we just go one step back. And we also echo the decision of the human by a put character, by essentially erase the character on the screen and then do a backspace at the screen. So now, if the back character is not given, but an ordinary character like an A or a B or whatever you have, then I'm going to store that in my R buffer. So here it is, gets at the R index position. If it's less than the buffer size, then I can increment the index because there's still space in my buffer. And in our setting, if you are at the very end, so if this condition is violated, you will just circle through. That's how we have done it. So you will overwrite and you start back from 0. Now, if the enter character has arrived, then the human is finished with typing a string in. So what happens? Clearly you echo the decision of the user back to its own console, but the R buffer now is going to be ending with an all 0. Why? Because strings in C need to end with the all 0 byte. So that's what we're doing here. Now we say that we're ready. We received the whole string, right? Because the return character was put in this else part. And we are going to, over here, turn off the receive interrupt. I'm only interested in that hardware interrupt mechanism, in the interrupt service routine, if I'm calling the getString procedure in my main program. Otherwise I'm not interested in it, because then I'm apparently not expecting anything. So I'm turning off the receive interrupt. So now we see how it works together. So we have 3 pieces. One is some initialization about how we're going to store the string in our buffer, which is defined like this. So that's initialization. We have a getString that is not doing anything really. It's just enabling the interrupt service routine and setting, some variables that control the state of what's going on to their default states, like I'm not yet ready, I still have to wait till I receive my string, and the index is set to the very first position in the buffer. At the global level, I need to have all kinds of, for the UART, for example, all kinds of control registers that I need to set. I need to enable global interrupts, whatever I use here. Then in this particular code, I'm interested in getting a string, for example. I have an infinite loop, that's how we always work. And we have statements like this. If a condition is met, I'm ready to execute a task, then you do it. But otherwise, try to find some other task that you can execute. For example, if this condition is met, I could execute this. I don't have to wait in my blocking fscanf for this while loop that I need to execute in my get character. So I can actually really make use of my resources in an efficient way. And here's the final piece. We have the interrupt service routine itself, which is just a simple line editor checking for getting a character with a backspace, a little more advanced. And effectively when it's called, you can immediately get the character from this register, right? And if you typed in the return character, it means that the string is finished. So you can now say that you are ready, you turn off the interrupt service routine, and you move forward. So that's it. So that's how these mechanisms work. So let me explain a little bit about, just for you to visualize maybe, or to think about it. Notice that the interrupt enable, right, is being manipulated in this interrupt service routine, and it's also manipulated in this getString over here. They are sort of nested, right? So the getString, if I'm calling that, I'm saying I'm interested in having the interrupt service routine to execute for me, because I'm expecting characters coming in, and interrupt service routine is enabled for as long as needed until you type in the return character and your string has finished. Then I can, turn off the receive interrupt, and because I'm not expecting any characters anymore. I only expect characters if I call the getString functionality. So that's one thing, and I like to really stress this programming style now. It's really important. We have this kind of infinite while loop, and we're just checking for whether certain conditions are met, and then the corresponding task can execute. Take another example. We will see, like, when the software clock counter has reached 1,000, meaning 1 second has passed, then display on the LCD screen something and reset that counter back to 0, and then at the background your interrupt service routines are incrementing that software clock counter. At some point it reaches 1000 again, and this is again called. And you can make a lot of those types of statements in here, and you don't really know which one of those will be executing next, only those in a round-robin fashion that are ready to execute, for which those conditions that are associated to them are met. So that's actually a very simple form of resource scheduling. It's like the way an operating system would work. Yeah, question?
So when this is going through, so that the get string function that runs first, that's the interrupt service.
Oh, yeah. Right.
So that runs, and that goes into the while loop, and then when the ISR is done, that if statement will go through?
That's exactly right. So let's go step by step here. So we have the get string. The get string is enabling the interrupt service routine. Then the interrupt service routine is now getting characters, updates the buffer, gets called again and again and again and again until I hit the return button. Then it gets in the else part. When that happens, it says I'm ready with my string, and I'm disabling the interrupt service routine. Now that it is ready, the while loop will at some point pick this up, right? It says, oh yes, already is equal to 1. There's a string waiting for me, and the task interpretation read buffer is doing something with its string. It puts it into some other variable, it's running some finite state machine, whatever you do, and at the end say I'm again calling the get string functionality. This is just an example. And when you do that, you again will go back to this statement. It says, hey, I'm interested in finding out a string, so let's enable interrupt service routine. And we go to the interrupt service routine. You get one character, maybe a backspace character, so that you actually remove one character from your buffer. But then you fill it up, and at some point the return comes in, and you will reset the buffer as well as you will end the buffer by putting the end of string symbol in C, which is the all 0 character. You say I'm ready, I'm disabling the interrupt.
So can you run other programs while this ISR is running?
You only run one program on your MCU, which is this infinite while loop. But while that is running, you're exactly right. Yeah. So now the get string. So look what happens. This get string is only doing this, and then you get out of the get string mode. Then in parallel, through your hardware interrupts, you're filling up the buffer with character strings. So in the meantime, at the same time, I can, for example, execute this one and then that one. Now, notice though that in a way there is no parallelism in your MCU. There are not multiple cores that can execute. But what happens is that it seems to be parallelized, because when I get out of this if statement over here, the get string has set the interrupt service routine flag, right? Like the enabling bit. So now if I'm executing this condition, say. Then I get an interrupt, oh, I got a character. Now I'm getting out of the interrupt service routine and again follow the while loop and do all kinds of things, LCD printing or whatever. Oh, I get another character. Oops, another one. So we type every 30 milliseconds maybe one character actually, or something like that. And the characters themselves take time to come in as well, right? But once they come in, they're ready and waiting for me in that register, and so the interrupt service routine executes for a very small amount of time. And then, for a much longer time, I will do whatever other computation I need to do, like computing averages over the temperatures that I've measured, what I want to display on my LCD screen, what I want to send out elsewhere. But once, after all those interrupts that sporadically happened, the string has finished and the ready flag is set to 1, then this statement can trigger in the while loop. And now this executes. and then this, but then it gets out again. So in other words, it seems parallel because the characters are being received through the interrupt service routine as sporadic points, and you make optimal use of the time in between when those characters are received by executing other conditions, other tasks corresponding to conditions. And it allows me to do optimal resource management.
So this is just to avoid the scanf waiting on that.
Exactly, because if I do that, then I cannot update my LCD screen. And that's very unfortunate if that is the case. Yeah. So that's what's going on here. I hope you will sort of, you will definitely play with this in the assignments and all that. And I think it helps to visualize to some extent what's going on. So one of the assignments that will come up, not today, but I think for Wednesday, we will have a hint, which is a diagram in which you can see what is being triggered when and what. And so you can see a little bit more of what is executing at what point. So everything is executing in sequence, but I just make sure I do not do any waiting. And I can reuse that time for executing other stuff. Yeah, we'll go over this a few more times throughout when we talk about timers and then later on stopwatches and all of that stuff, which is next block for the stopwatches. Yeah. All right, cool.